Well, hello again. In this video, we're going to pick up the discussion of the Jacobson radical of a module and a ring from where we left it last time. And last time we proved the following two facts. The first one says that the Jacobson radical of a module is sort of invariant under modular homomorphisms, from which it follows that the radical of the ring R is a right module over itself is a two-sided ideal. Okay, now there's another fact that follows from the first assertion, which we will use later on, namely this. The product of a module M and the Jacobson radical of the ring considered as a right module is contained again in the Jacobson radical of the module. For those of you who are not familiar with what the product is, here's its definition: simply the collection of finite sums of this form, finite products of this form, sums of finite products. And it can also be viewed like so. I'll encircle this to highlight the fact that the reason for the inclusion, is simply that the left multiplication by a fixed element of M constitutes a module homomorphism between R itself as a module and M. So Mj would simply be the image of J under such a homomorphism. Then the inclusion should follow easily from the first assertion there. Well, one question that comes to mind is what the relationship between the left and the right radicals of the ring are, namely the radical of it as it's considered as a right module, and the radical of it as it's considered as a left module. So how are they related? Before we answer this question, let's note the following proposition, which is quite handy. The following are equivalent for any right ideal A of R. A is contained in the radical if and only if for every element A of capital A, 1 minus A is right immutable. This means 1 minus A times an element of R is equal to 1. And 3 is a little strong, actually much stronger version of the 2. It says for every A, 1 minus A is actually invertible, which means right and left invertible. So let's prove this. First, let's get the 1 implies 2. Given any element A of capital A, assuming number 1, of course, A being a member of the radical, AR is small in R. Remember our characterization of the radicals elements for any module. The Jacobson radical is simply the submodule generated by non-generators, which in case correspond to those who generate cyclic small submodules. So, which is why AR is small in R. Well, notice that AR plus 1 minus A is equal to R, and by smallness 1 minus AR must be all of the ring R. But then this means there's an element R such that 1 minus A times R is equal to the 1, the unity of the ring. Therefore 1 minus A is right invertible. Okay, as for 2 implies 3, let's remember the hypothesis in 2. For every element A, 1 minus A of capital A, 1 minus A is right invertible. How are we going to get that 1 minus A is actually furthermore invertible? So, take an arbitrary element, let's say x of A. Since by our hypothesis, 1 minus x times y is equal to 1 for some element y of R. Well, expanding that equation, that equality, we get y minus xy is equal to 1. Now what we are going to do, we'll try to prove that this y is actually right invertible as well. Once we do that, the result will follow very easily. So, well then, if we write, then we can write y as 1 plus xy, which simply is 1 minus an element of a, and thus y is right invertible. So how are we going to get that 1 minus x is two-sided invertible? Well, by hypothesis, the y is right invertible, as I said, and say by some z, which means there's an element z such that yz is equal to 1. Now, if you multiply all three elements, 1 minus x, y, and z at once, first it's going to give you 1 minus x because yz is equal to 1. And then next, it's going to give you z, the same product, because 1 minus x, y, z is equal to z. I'm sorry, that should be, yeah, it's equal to 1. 1 minus x, y is equal to 1, therefore you get z. Okay. So if we read the beginning and the end of this whole argument, we get 1 minus x equals z, therefore 1 minus x and therefore y is the right and the left inverse of 1 minus x. Therefore 1 minus x is invertible, as desired. Let's prove 3 implies 1. 3 says for every a, 1 minus a is invertible. Actually, this simply implies 2, and the proof that we're going to present here actually proves 2 implies 1. So, take an element a of a, we want to prove that it belongs to the radical. Now, in order to prove that, it simply suffices to prove that AR is small. So assume AR plus B is equal to R. Well, then this means there's an element R of R and B of B such that AR plus B is 1. But remember our assumption, so AR is an element of A, right? So this means 1 minus AR, which is equal to B, is right invertible or invertible. But once it's invertible, then 1 belongs to the submodule generated by B, which in turn is contained in the larger B. So the capital B has to be equal to R because it contains the generator of R. This completes the proof. So this is the end of the proof. Now we have a corollary. A corollary which settles the relationship between the two radicals, Jacobson radicals, namely that of R as a right module and that of R as a left module. It simply says that they are equal. What I said is actually corollary 2, but how I say it is through corollary 1, which says that the radical of the ring R as a right module is the largest right ideal satisfying 3. This one follows from the previous proposition immediately. Once that's true, notice the fact that both radicals are ideals, and each one now satisfies the property 3, which is sort of symmetric. So what the proposition does for us in this case is to afford this symmetry through which I can pass from the radical radical of R is a right module satisfying condition 3 to radical of R is a left ideal. Okay, I think that's pretty neat and easy to understand. So now that the two radicals are the same, then there is no reason to distinguish between the right and left. So now we give the common name, the Jacobson radical, to both of them. So we'll simply call it the Jacobson radical, and we will denote it by J. Now, there are two notions that we will need here to work our way toward the Wedderburn-Artin. One is the Jacobson semisimplicity, as distinguished from the semisimplicity of a module. This is when a module, or a ring in this case, has 0 Jacobson radical, which means the only small submodule is 0, and there are no the intersection of maximal submodules is simply 0. And then there's the notion of an Artinian and Noetherian module. This is the content of the second definition. An Artinian module simply means, well, I said R here, but it actually applies to modules as well, and I think we will point this out in a later slide again. So take a module R for the general effect. Let this R be replaced by M. If any descending chain of submodules of M must eventually stabilize, which means it will stop strictly decreasing after an index such as n0, then we call this module Artinian. In the case of R considered as a right module, we call it a right Artinian ring. Similarly, a left Artinian ring is defined, and instead of the descending chain, if we said ascending chain, then the ring or the module would be Noetherian. So as I said, if we replace descending in the above definition by ascending, we get the Noetherianity. Again, this could be considered for the module case in a more general fashion. So there are two types of things now, two types of modules, Artinian modules and Noetherian modules. What is the difference between them? Well, Z as a module over itself is right Noetherian, obviously, and Jacobson simple, semisimple, but it is neither Artinian nor semisimple in the sense of the Wedderburn. So, for example, Artinianity or Noetherianity alone don't imply, and/or we could say, do not imply the Wedderburn semisimplicity, namely being a sum of simples. But for a finitely generated module, which we will point out later in this more general form I mentioned, in particular for a ring, for example, considered as a module, if a ring is semisimple, namely if it is a sum of simple right ideals, then it's Jacobson semisimple, namely its Jacobson radical is 0 and it's right Artinian. In fact, it's right Noetherian as well. Now, let's look at an example which is not a semisimple ring. This ring, the ring of upper triangular matrices where F is a field, I should stress that it's a field, otherwise it wouldn't work, this result. This ring is right and left Artinian, so it's Artinian as a right and left module, but it is not Jacobson semisimple. So Artinianity alone doesn't guarantee Jacobson semisimplicity. Okay. So looking at the examples here, in fact, you could look at more and more examples, you would still observe the same phenomenon, namely that all the right Artinian rings appear to be Noetherian at the same time. So now we ask, naturally, if this is a general fact. Before saying yes or no to that, let's remind you of the module generalization of the general case of the Artinian Noetherianity defined for modules once again. And now we can get to the answer of this question, I guess. But let me stand corrected. In the next slide, what I'm going to do is this. We said that a finitely generated semisimple module, for which we gave the example of R being semisimple, such a module is Artinian and Noetherian. We will prove this. We will actually indicate a proof of this later on. The converse of this would read a semisimple module being Artinian or Noetherian. Is this true? So we are going to look at these questions all together. In the next slide, we're going to give a condition, along with Artinianity, that guarantees semisimplicity in the Wedderburn sense. So here's our proposition. If M is an Artinian module that is Jacobson semisimple, namely with 0 Jacobson radical, then M is a semisimple module. As for the proof of this, first note or recall the fact we established, namely that semisimplicity of a module is equivalent to every submodule being a direct summand. So you take a take any submodule A of M, and assume A is non-zero, because if A is 0, then it's already a direct summand. So if A is non-zero, then A is not a small submodule, because the module is Jacobson semisimple, right? So it cannot be in the radical. Then the set of submodules B of M, whose sums with A are all equal to M, is non-empty, right? So then by the Artinianity assumption, we can choose a minimal element of gamma, called B, and notice that A intersection, this minimal element B of gamma, is small in B, because if A intersect B plus C is equal to B, then adding A to both sides, A intersect B would merge into A, therefore A plus C would be equal to M. But then A is okay, but this would contradict the minimality of B as a module whose sum with A is equal to M. So, which is why A intersect B is small in M, but then, oh, I said it's small in B. But then once it's small in B, it has to be small in the even larger module M. This is easy to see. Therefore, A intersect B is equal to 0. So we have A direct sum B equal to M as desired, making M a semisimple module. Well, one important corollary of this is a part of the Wedderburn-Artin. If R is a right Artin ring that is Jacobson semisimple, namely with a 0 Jacobson radical, then R is a semisimple module as a right module. We will have a more refined rephrasal of this statement. But for the moment, let's just say R is semisimple as a right module in this case. Let's recall what this proposition said, really, the one that yielded this corollary. An Artinian module that is Jacobson semisimple is semisimple. How about the converse? If M is semisimple, then is it Artinian, and is it Jacobson semisimple? With a little limitation, the answer is yes. So the converse of this proposition is the following. If M is finitely generated and semisimple, which means it's a direct sum of finitely many simple modules, then M is Artinian, and it's Jacobson semisimple. Okay, let's give a couple of clues for the proof. I say one clue, but it's actually two. To prove this statement, namely finitely generated and semisimple modules are Artinian and Jacobson semisimple, first observe that any finite sum, and not necessarily direct, of course, just any finite sum of Artinian and Noetherian submodules of a module is again Artinian or Noetherian. It's a fun exercise to prove. Now this, along with the fact that the radical can be distributed over a direct sum, will work the proof, will establish the proof. Well, how does this follow? If you wonder how this follows, here's a simple way to look at it. First of all, we said in an earlier slide that a small submodule of a submodule is small in an even larger module. What does it mean? It means if A is small in B and small in... If A is small in B, which is a submodule of C, then A is small in C. So this means the radical of M alpha, each M alpha, which is the sum of small submodules of M alpha, is contained in the radical of the larger module, which is the direct sum. That's what it means. Okay, so this settles one direction, namely the inclusion of the right side and the left side. As for the inclusion of the left side and the right side, let's first take these back. Okay, the way this works, I'll give you just one clue about this. I'll remind you that radical is preserved, Jacobson radical is preserved, not preserved in the sense that it is taken into the radical of the codomain module under homomorphism. So this fact and the use of a proper homomorphism or many proper homomorphisms, I'm sorry, I said proper, I meant appropriate. The use of some appropriate homomorphisms, one for each alpha, would settle the direction from left, the inclusion of the left side in the right side. Remember, we raised a question as to whether Artinianity or Noetherianity imply each other. The answer for one of these was no, clearly, given by the example of Z, which showed clearly that Noetherianity doesn't imply Artinianity. But what about the converse? Well, there are two answers to this question, one in the module case and two in the ring case, whether Artinianity implies Noetherianity. The answer is no in the module case and yes in the ring case, ring considered as a module. So let's prove that. Let's look at that. As for the module case, here's an example of an Artinian module that's not a Noetherian. This is the well-known Prüfer group, and it's simply the subgroup of Q over Z generated by or consisting of elements of this form for a fixed prime P. Here n and a are variables, variable in Z, naturals and Z respectively. Also note that, I mean, this Prüfer group is a quite intriguing object in the sense that Q over Z, first of all, is the direct sum of all these Prüfer groups as P ranges among primes. And two, every proper factor of the Prüfer group, every proper factor, is again isomorphic as a group or as a Z module, they are the same as you know, itself. So every proper factor, every factor which is not trivial, which is not zero, is isomorphic to itself. That's a strange phenomenon. And this is a good example in our context as well, because it gives us an Artinian module which is not Noetherian. Artinianity could be, well, all this can be seen in this picture of all the submodules lined up in this fashion. This chain, this sequence, shows all the submodules of ZP infinity, that's the Prüfer group, as forming a chain. Well, you may wonder why I use a ZP, or ZP square ZP cube, which I reserve for integers modulo P square P cube, because it's exactly their copies that I'm talking about. For example, ZP stands for any module, any cyclic group with order P, ZP square any cyclic group of order P square, and so on. So copies of these things are lined up in this fashion, forming a chain of submodules, and the only submodules, all submodules of ZP infinity. So you see that it is not a Noetherian because this chain doesn't stop, but it is Artinian, the ZP infinity, because any submodule of ZP infinity is one member of this chain, which if you go to the left, slightly left to the left of the module ZP infinity, you will hit a ZP to the n. Therefore, there will not be much room to go infinitely below, because it's a finite submodule. So every submodule of ZP infinity is finite, except itself, of course. So this is a good example, defying the implication Artinian implies Noetherian in the module case. How about the ring case? Before we can establish the ring case, before we can establish it, Let's prove a lemma, actually a couple of lemmas. The first lemma is the following. If R is right Artinian, then the Jacobson radical is nilpotent in the sense that j to the n is equal to 0 for some natural number n. And the factor ring R bar, which is defined to be R over J, is semisimple in the Wedderburn sense. Now, before the proof of this first statement, the one about the R bar, remember our corollary which we proved a few pages ago. The one that says if R is right Artin and Jacobson semisimple, then it's a semisimple right module. Now let's go to what we want to prove. Here it is. I said first part, I guess it's the last part. Anyway, so the part about the R bar. R bar is now with 0 Jacobson radical. It's very easy to see by correspondence. And since R is right Artinian, so is R bar. Therefore, R bar is a ring with 0 Jacobson radical and it's right Artinian. So it is a semisimple right R bar module. As for the nilpotence of the Jacobson radical, first note that the powers of the Jacobson radical form a decreasing sequence which must stop at some point, say n, by the Artinianity of the module, of the ring. Now we claim that the place where it stopped, namely the nth power, it's simply equal to 0. J to the n is equal to 0. Let's prove that. If it is not equal to 0, once again, if it's non-zero, namely j to the n, then by Artinianity, the set S, which we define to be the set of all right ideals whose product with j to the n is non-zero, which now is not non-empty because j is an element of S. This set has now a minimal element because of Artinianity. Let's call it A. And what this means is that A times j to the n is non-zero. So, and what that means, that in turn means, is that there's an element, small a of capital A, such that this equality holds. Namely, R times j to the n equals aj to the n, because R merges into j to the n, and that equals aj to the n plus 1, because this is where the above sequence terminated. And all these are non-zero. But then, you see, we picked A as a minimal element of S, therefore, by that minimality, AR, AJ, and capital A must all be the same thing. Now, what concerns us here is the equality of these two. Now, unless AR is 0, which of course will be a contradiction, unless it is 0, the equality of AR to AJ is a contradiction. Now, why is that? That's because AJ is supposed to be small in AR, because AJ is contained in the radical of a finitely generated module, which in this case is AR. Therefore, it would normally have to be small in AR, but it's not. Turns out it's not unless it is 0. But then this constitutes another contradiction, namely to the fact that A is by choice non-zero. See this line over here. So we end up with a contradiction. This settles the result, except the part where we are supposed to explain why AJ is small in AR. Here's a small sketch of the fact, the details of which I'll leave to the viewer. AJ is obviously inside, well, it's equal to, okay, let's put it this way. AJ is equal to ARJ. Remember mj, so this is in the radical. The underlined part, I said it because I was alluding to the result on the first page, the one that said mj is contained in the radical of m. So here this is in the radical of AR. But then the radical of AR is a sum of small submodules. And it's going to be a finite sum because it is AR is finitely generated. Now, the fact that a finite sum of small submodules is again small is your exercise, for those of you who are interested. So this is your exercise. Now we continue, we erase all this and continue. Remember, we are doing all this to prove that Artinianity implies Noetherianity in the case of a ring. And we will do with a little less. We'll do a little more with a little less. We will do a little more using a little less. Artinianity is just too strong for me right now, for what I'm going to say. So this is the next proposition. If R has nilpotent Jacobson radical and R by J is a semisimple ring in the Wedderburn sense, on the right side, let's say, then the Noetherian R modules and the Artinian R modules are the same class. Okay, here's the proof. Take any module. For the beginning, take any module M. And assume that N is an index which satisfies the equality J to the N equals 0. Then we have a descending sequence of submodules. And which has to end with 0 because J to the N is 0. Okay? Now, look at each factor of this sequence, by which I mean each element, each term divided by the one on the right, namely mj to the k over mj to the k plus 1. This is a module and annihilated by the Jacobson radical, which means this. And therefore, it's canonically, this factor module is canonically a module over R bar, namely R over J. And as an R, okay, it's submodules as an R module, and submodules as an R bar module are the same. Okay? And since it's now a module over R by J, this factor and since R by J is a semisimple ring in the Wedderburn sense, on the right side, for the moment I'll keep saying on the right side until we establish they are the same thing, right and left. It's a right and left symmetric argument. Until such time, let's keep this terminology. So it's a module over a semisimple ring, therefore it is itself semisimple. Now, how does Artinianity and Noetherianity factor into this? If M is any one of these two things, Artinian or Noetherian, I say respectively, but, well, just pick any one of your choice. Then this means each factor, mj to the k over mj to the k plus 1, is a finitely generated semisimple module. We have already established that it is semisimple. Now we are saying it's finitely generated because any of the conditions, Artinian or Noetherian, implies on a semisimple ring finite generation. Okay? So now we have mj to the n equal to 0, and each, let's say mj to the n minus 1 over mj to the n, both Artinian and Noetherian. So what we are doing here at this point is we are carrying out an inductive argument starting with the very end module, that's mj to the n, and the factor mj to the n minus 1 over mj to the n, and working our way up, again inductively, toward the m in the sequence we saw a couple of slides ago. So for example, in the nth case, mj to the n is 0, and mj to the n minus 1 over mj to the n is Artinian and Noetherian, because it's a finitely generated semisimple module. Therefore, it is both Artinian and Noetherian, which implies mj to the n minus 1 is Artinian and Noetherian. Now, iterate this argument for mj to the n minus 1 replacing mj to the n, and the next factor of the next factor to the left of n, the nth term. This will give you mj to the n minus 2 being Artinian and Noetherian, so on and forth until we get m is Artinian and Noetherian both. So now we can state what we want merely as a corollary. A right Artinian ring has to be right Noetherian, but of course the converse doesn't hold because of, say, this example. This ends today's video. Thank you for listening.